Okay. So last time we discussed about the gas laws, and after that we learned about the uh, ideal gas equation. And from actually from last week, from the before week, we started learning about the ideal gas equation, then Boyle law, Charles law, Avogadro's law, and we learned about the Dalton's law of partial pressure. And we did some questions regarding that. Okay, remember? Right. So we have come to an end of the first part of this lesson. So the first part is regarding the gas. Now today we are going to start discussing the new part of this lesson, that is the molecular kinetic theory. Right. So today we are going to learn about the molecular kinetic theory of gases. So that is the today's topic. Molecular kinetic theory of gases. So let's see what we are going to learn under this molecular kinetic theory. So under the molecular kinetic theory, actually we are learning about the kinetic energies, and the way the molecules behave in usual situations. Right. So that's the thing that we are going to learn under this. To apply the molecular kinetic theory, we need some assumptions. So let's start learning about those things. Right. So those are the things that we are going to learn. Right. Now, under the so what are the assumptions that we take that we have taken under ideal gas equation? Yes, exactly. Yeah. How do they act as ideal gas? How do the gases act ideally? Yeah, we learned that the gas particles are unit masses with no intermolecular forces in between each other. So that was learned under ideal gases. So that was a property of ideal gas. Now here also we are learning that gases are composed of widely separated large small particles. Right. So that is one of the assumptions that we are means uh, each gas particle under gas particles they undergoes random motion. That means each gas particle can and each other and with the walls of. Is it clear? The second assumption of the molecular. The average kinetic energy of gas particles that ideal temperature. Okay. Right. Ideal. The gases behave as ideal gases. Fifth one, the pressure of the gases arises from the sum of the collisions of the particles with the walls of the container. So, as I have told you earlier, the particles they move in straight line motions and they collide with the walls of the container. As a result, due to that force, they will exert a pressure. Is it clear? Right. So, those are the 5 assumptions that we are taking under this molecular kinetic theory of gases. Right. Right. So, let's learn about these about this molecular kinetic theory in detail. Did you write about the molecular kinetic theory of gases? Right. Right. So then let's explain what this molecular kinetic theory is. You can note down. You can note down the gaseous systems. The gaseous systems behave differently. The gaseous systems behave differently under different conditions. The gaseous systems behave different under different conditions. So different gases show different gases show different observations. Different gases show different observations at different conditions. Then we can say to the same point we can say the experimental observations of these gaseous systems of different gaseous systems are explained with the help of this molecular kinetic theory. Right. Now, for example, don't write this. For example, now let's say we are compressing gaseous system at a constant temperature. What will happen? Let's say we have a gas station. So we are closing the open end from your thumb and we are compressing. We are pushing the piston in. then what will happen? The gap under the volume is decreased. No? Once we press it, the volume reduces. No? So the volume is decreased. Now that's the observation that we make. But during that volume decreasement, there are some molecular level change that will take place inside the gas. That means the gas molecules will behave differently. So that change is being explained with the help of this molecular kinetic theory. Not only the volume, the other parameters also can be explained with the help of this molecular kinetic theory. Is it clear? Right. So then you can note down separately in a separate point. Why I did? Now we are talking about tools. For that. The other one, RIS people are very public. Yeah, they keep texting me that they are coming. Right. So let's write in a separate paragraph. Therefore, the gas laws help us to predict therefore the gas laws help us to predict the changes that will happen the changes that will happen in the molecular level of a gas. So the theoretical model, that is required or that is developed the theoretical model that is required to explain such events and to explain the behavior of gases the behavior of gases at the molecular level. Behavior of gases at the molecular level is known as the molecular kinetic theory. Is known as the molecular kinetic theory. So that is the definition of the molecular kinetic theory. The theory that we use to explain the behavior of gases at the molecular level. That is called the molecular kinetic theory. Is it clear? Right. Then the next subtopic you can write down assumptions of the molecular kinetic theory. assumptions of the molecular quantity theory of an ideal gas. Assumptions of the molecular quantity theory of an ideal gas. Right. As I explained you at the start of the lesson, there are 5 assumptions. Can you remember at least one? The first one I did that the gases are composed of widely separated large number of small particles. That is the first assumption. Yeah. Okay, so let's write these assumptions. So number 1. You can write down the first assumption. Gases are composed of widely separated large number of small particles. Large number of small particles within brackets, atoms or molecules. Right, so let's explain this one. You can write down. Because of this large separation of another first assumption. Because of this large separation of the particles, the actual volume of the gas particles is very small. Actual volume of the gas particles is very small when compared to the total volume of the gas. When compared to the total volume of the gas occupied. Basically, right. So in other words, we can say that the total actual volume of the molecules is negligible when comparison to the volume occupied by the gas. Is it clear? Right. So that is the first. Right. Right. Now, due to this reason, we can say that the gas particles are widely separated. Okay, so they have relatively very low densities when compared to liquids and solids, because the particles are arranged far away from each other. They are far apart from each other. Is it clear? Right. So then under that paragraph, you can write down to the same point. Due to this large separation of gases, they have relatively low densities. They have relatively low densities than liquids and solids. Relatively low densities than liquids and solids. So therefore, So they are the high compressibility of gases. The high compressibility of gases can be explained. So that is the first. Is it clear? So the first one is the gases are composed of widely separated large number of small particles called atoms and molecules. Then the second is nothing right now. Each particle of gas each particle of gas undergoes motions. Each particle of gas undergoes random motions, which are straight line motions. They are straight line motions. Straight line, yes, straight lines. They are straight line motions. And the collisions between the gas particles and with the wall of the container are perfectly elastic. Elastic. They are perfectly elastic. What do you mean by elastic? Not stretching. Actually, not exactly stretching. Stretching is there. Stretching part is also there. What do you mean by elastic? Elastic can store potential. Yes, potential to store. So once the force is applied, they will be elongated, and once the force is removed, they will come back to the original position. So that is called elastic. So if you get a rubber band and pull it, what will happen? If you get a rubber band and pull it to the opposite side, it will get elongated. Once we release the pressure, it will come back to its original shape and the position. Okay, basically, if we take a clay ball, a ball of clay, what happens if we apply a force? There will be a permanent deformation, no? And once the force is removed, it will not come back to its original. So that is for elastic. In the elastic processes, there is the energy is conserved. Now these gases, the collisions of the gases are also elastic like that. That means initially the reactant gas molecules will have a particular amount of energy. Once they are mixed with each other, they will hit with each other. That means they will collide with each other, and the total energy in the system will remain the constant. Each and every individual atom or molecule will gain or lose energy, but the energy of the entire system, it is not wasted. Okay, so that is the second assumption. Right. Then you cannot to the same point you cannot down. Energy may be transferred energy may be transferred From one particle to another, energy may be transferred from one particle to another. Their individual energies may change. The energy of one particle transferred to another particle, but their individual energies may change. Come on. But there's no net loss of or gain of energy. But there's no net loss of there's no net loss or gain of energy. Right. So that is the second lesson. The third one you can write down. The average kinetic energy of gas particles. The average kinetic energy of gas particles depend only on the absolute temperature. The average kinetic energy of gas particles depend only on the absolute temperature. Right now, we know that the kinetic energy of a particle that is half mv square. So m is the mass of that particle and v is the speed of that particle. So then for gases, kinetic energy equals to 3 out of RT. R is universal gas constant and T is the absolute temperature. Is it clear? Right. So that is the equation that we can use for gas. 1 mole of gas. No need to worry. We will be deriving this equation in the latter part of this lesson. Then you know how to derive this. You can write these two equations for now. I'm not going to be. Sorry, being on the show. I'm not sure. It is 18 from the morning. I don't know it. Right? Is it okay? Finish. Then that is the third assumption. Then you can write the fourth one. Gas particles behave independent. Gas particles behave independent. But that means each and every gas particles they will move independently, and then they tend to collide with each. Then the next positive and fifth one, the last one, pressure of a gas pressure of a gas arises from pressure of the gas arises from the sum of the mass of the particles pressure of the gas arises from the sum of the collisions of the particles with the walls of the container. The walls of the container. Right. So this postulate explains the Boyle's law, no? Pressure temperature relationship. No, not the pressure temperature, pressure volume relationship. The temperature is constant. That means smaller the volume, there will be more frequent collisions in a gas particle, and larger the volume, there will be less frequent collisions. So what will happen once we reduce the volume? Pressure increases, and there will be more successful collisions. So that means at higher pressures and lower volumes, the gases will react very fast. Is it clear? So if it explain that positively, you can say for the same amount of a gas, for the same amount of a gas, comma, the volume for the same amount of gas, the smaller the volume of the container, and the smaller the volume of the container, there will be more area. There will be more collisions per unit area. The average distance traveled by a gas particle before collision before the collision is less in the smaller volume. is less in a given volume. Therefore, more collisions will take place. Therefore, more collisions will take place in a given volume. Producing a higher pressure. Then I can say the more the gas particles, the greater the frequency of collisions. So higher the pressure. Right. So there is a summation. Let's learn about the equation of the molecular kinetic theory. So that is about the molecular kinetic theory. Now here, as I have explained to you, right? In the molecular kinetic theory, we are learning the molecular level behavior of the gas particles. Is it clear? We are explaining the molecular level behavior. Now for this, we have an equation that is called the equation of the molecular kinetic theory. You can write it from topic equation of molecular kinetic theory. Equation of molecular kinetic theory. Right. So here we have an equation like hydrogen equation that is PV equals 1/3 MC square. Okay, this is the equation. There P is the pressure. In pascals. V is the volume in cubic meters. One that those are digits. M is the mass of a gas molecule. Capital N. Number of gas molecules. Then C square bar. C square bar means we call this mean square speed. Mean square speed, or we can say mean square velocity. Right. You can write the equation and name the parameters. Okay. Right. So in this manner, see, we have identified the parameters of this equation of polynomial. There's a new thing that is the mean square speed. Now let's see how to determine this mean square speed. Okay. Right. So you can write the next of mean square speed and the mean speed. Mean square speed and the mean speed. So now it is worthy that we know the definitions of these ones. Mean square speed and mean speed. Uh, so it's like this. Now we can do the average speed. Like you can note down. Another way you can write down. Consider a sample of gas particles. So consider a sample of gas particles. Consider a sample of gas molecules with different speeds of like this. Now in this sample we have n number of gas molecules. So we have n number of gas molecules, each are having different speeds. So they are changing from C1 to Cn. Basically. So then here we can take the average speed. That is sum of the total speeds divided by number of molecules capital. So that is the average speed. Is it clear? Sum of all the speeds divided by the numbers of molecules present will give the average speed. Right. Then we can say that the average is the mean speed. Right. Then let's find out the mean square speed. Like this. That is the mean square speed. That means we are squaring the speeds and taking the mean of that. Then there's another parameter you need to know, that is root mean square speed. Actually, the average speed is called C bar. With this C square. Another one is root mean square speed. It's like this. So that is the square root of C square. Is it mean? Like this. So that's the other thing that you need. So these are the important things we can complete. Which sorry, mean square speed. We square speed, yeah. Square speed. And then do the same ones. If we just answer the square root was applied to the number of moles. Yeah. Then we mean square speed is different. Root mean square speed is the square root of that. Those are not the same. I think I am. Yes. Do we have that?
Tomorrow. From these three things,
My face TV was the recording.
I was the recording.
But that's not recording. Just go on and do it. You requested me with one. Yes, that was last week. I'm with this now. Yeah. In the morning, you asked me to going on like yes. I said yes. I can't see it like it's suffocating and can you say maybe it's up in close to yes. Did you copy that? I'm sorry. Should take about 20 minutes. Why house? Hey. What non? Quiz. Ah, quiz era. But no, he is going to the reason. Do you want to read
Either really like the time or sense and way. Or betting, betting as we need to
He's got an answer.
answer you keep it here. We guys will go to the last one.
So since you have got an idea about this root mean square speed, square speed and average speed. Yeah, that is a mathematical thing. That means it is to minimize the amount of errors that will take place.
Take average.
The speed has an average distribution of like this. These molecular speeds are in a distribution like this. So it's not fair to get the average of this. See, these are not smooth. This is not a smooth straight line curve even. Like this. That's why I told that this is a mathematical one. So we are not teaching you the mathematics part here. Just remember that we are taking the square speed. Bar means the mean.
Yeah, we make it minus. Like, do we see
No, C bar means average speed. That means the mean speed.
so the answer is negative, right?
No.
I mean, bar means opposite.
No.
Here is decimals.
Okay. Now these are statistics. These are statistics. Now we know that we have maths. The maths have been developed for so many centuries by the people, by the mathematicians, and there are very nice things in the maths. So we are just learning few of them in A levels. So under the statistics part of maths, this is the simplest thing that we learn. Sorry. Yeah. So this is the average speed. Average speed. Now we know that for anything the average is sum of the values divided by the numbers of values. So that is represented by the symbol C bar. It's a simple.
Bar means opposite. So bar means decimal. It means open up my water. Bar
So there are different applications. Here in statistics, bar means mean. Okay. Take a matter. Sorry. No, it's not a decimal. Now you have confused it with logarithms, right?
Exactly.
Yeah. In logarithms, we have bar. So don't get confused with logarithms because we are not having values already. There are values. Those are different. Now, just remember that C bar means the mean speed or the average speed. Okay. Right. Now we can use the molecular kinetic equation to show how the temperature depends on the mean square speed of a particular gas. So that's the thing that we are going to learn. In a separate point, you can note down the equation of molecular kinetic theory. The equation of molecular kinetic theory can be used the equation of molecular kinetic theory can be used to derive an equation to show the temperature dependence of the mean square speed. So the temperature dependence of the mean square speed. There is no doubt. Consider the gas. Consider a gas under pressure capital P. Under pressure capital P. Volume capital V. And having capital N number of particles. Right. So that we can apply the equation of molecular contact theory, that is PV equals 1/3 MNC square. Okay, so that is the equation that is given. Is it clear? Right. Then N is the number of molecules, and we know that N is equals to simple simple N times Na. What is that? What is simple N? Simple N is numbers of moles. Simple N, yes, number of moles. Number of molecules is capital. Yes. In this equation, what is N?
Number of molecules.
Moles.
That capital.
Capital N is number of molecules. Yes, I am asking simple N.
That is
But it is me. Yes, that's what it shows. Now we know that the number of molecules equals to number of moles into Avogadro number. Because we know that one mole has Avogadro number of molecules. Okay, so in one mole we have Avogadro number of molecules. So in 2 moles we have 2 times the Avogadro number of molecules. So if there are n number of moles, it is number of moles into Avogadro. So there we know that number of molecules equals to number of moles into Avogadro number. Yeah, we can use L if you like. But you can use NB. So therefore we can say PV equals 1/3 into M into number of molecules equals to N in A. 10 times in A into C square bar. Is it clear? Did you get it? There is another relationship, that is the molar mass of a given substance equals to mass times Avogadro constant. Is it clear? Then we can replace this M and in name capital N. So we can say PV equals 1/3. So M into NA is capital N. And N is there. C square by is there. So then PV equals to 1/3 capital M in C square. You can simply write it as PV equals 1/3 M in C square. Then there's another relationship. Ideal gas equation, we know that PV equals nRT. So let's take this as the first equation and this as the second equation. Is it clear? Then we can equalize 1 and 2. Why? PV is a common thing. So 1 equals to 2. There we can say 1/3 M and C square bar equals to nRT. Then simple n can be cancelled off from both the sides because it appears on the both sides represent the same thing. numbers of. So they are. We can subject c square bar because now we are going to express the root. We are going to express the mean square speed. So c square bar equals to 3. When it comes to this side, it becomes numerator 3 RT divided by capital. Is it clear? So therefore, we can give the root mean square speed equals to 3 RT over capital N square. That is the expression for root mean square speed of the gas molecules. Is it clear? This equation to find the speed of a gas molecule.
I think we can use the equation of the time.
Which one?
P equals to
P equals 100 mc square bar. Can we count the number of molecules? Come on, now we are learning these equations for the practical applications, not only for the exam. For the exam, they will be giving you particular value. But if you are going to do a research and find these values, so the most easiest thing is now for a particular gas, we can determine the molar mass. Okay. And R is the constant, and we can measure the temperature. Then we can easily find the root mean square speed of that particular substance.
we derive this in a equation.
Maybe. Now, all these equations that I give you in boxes, you can apply directly. If they are, that means if they have asked you to derive the equation, then you have to derive.
If they ask to derive, the usage should be.
Yeah, not to use it, you don't need it. So there we can see that the root mean square speed depends on what? Square root of the absolute temperature, no? Because all these are constants. Therefore, we can say this. C square bar root proportional to absolute temperature, square root of the absolute temperature. Right. You can copy it down. Just thinking, what is this now? What's the use of learning this?
If we consider radicals have distance like x weeks.
Sorry,
X
I didn't hear.
X week.
What?
You can't produce.
Yeah,
There's x weeks.
yeah,
Which is a distance like actual goes.
yeah.
If that happens, it's been different.
That might be different. But all these things are derived before the quantum mechanics.
Then you consider you that's factor.
Yeah, you don't consider. Right. So that is how we represent the temperature dependence on the mean square speed of root mean square speed of a gas. Then what will happen once we increase the temperature? Speed will increase. If we decrease the temperature, speed will decrease for the same gas under same conditions. No? For the same gas, why? Because then the molar mass will be the same. If we use two different gases, then the molar mass too will be changed. Huh? So it too will be a factor which determines the root mean square speed. Is it clear? Right. So let's see a small question. Why?
Small question.
No, no, small one. You can note down the question. Calculate the root mean square speed of calculate the root mean square speed of hydrogen gas at 25 degrees Celsius. Can you do it or shall I do it? Can you do it? Now you need to find out the root mean square speed, so you can directly apply this equation. Very far. 8.31 for root mean. What is that? Universal gas constant, I got it before. Yes. It's 8.31 for joules per moles per Kelvin. Hydrogen, what is the molecule? H2. H2. So there are two hydrogen atoms. What's the molar mass of one atom?
One.
One. So if there are two atoms,
So we are dropping one hydrogen atom of the compound.
why do we need to drop it?
And if you find like this, are we dropping the molar mass of the element? The whole thing.
That's how. It's a whole compound. It's two molecule. Right? Did you find the answer? What is it? How is it? Still? Right. Answer was it.
I mean, I didn't find the. Yeah, sir. I guess. I mean,
Come on.
there. I mean, root area.
Now see how we are going to simplify this one. I taught these short techniques during last videos. Last weeks, yeah. Yeah,
No, I didn't told last night.
I have taught this. Now you will remember. So we can use this equation directly. C square bar square root equals to 3RT over M square root. Then for hydrogen we can say C square bar square root that is 3 into R is 8.314 joules per moles per Kelvin. T is 25 degrees Celsius means 298 Kelvin. Divided by molar mass is 2 into 10 to the power minus 3 kilograms per mole. Square root. Yes. You can't just use 2 because we have to apply in kilograms. SI unit of mass is kilograms. Always if you apply SI units. Haven't I told you that? Haven't I? Or have I?
Yes.
Alright, yes. Both can apply, but I do an Then other one is now see 3 into 8.314. I asked you to take it as yes 3 into 8.314. I asked you to get it as 25.
Oh, that big on the big.
Yeah, that is another I got it. Yes. So no need to simplify, no need to calculate. Into right. See 2 times 298. It is divisible by 2. It has to be 149 into 10 to the power 3, right? Alright. Then you have to simplify this one. What's the answer? Come on, what's the answer? You just need to multiply 149 by 25. Yeah. It's 3,725. Into 10 to the power 3, that means 3 zeros. Right. Then we need to get the square root of this. Yes. How do you get the square root of that? You can simply use a long division method. Answer will be 1930.02. So we can approximately take it as 1930. Meters per second.
Insert.
In what?
Insert.
Insert. That is not exact.
So is it Shani copies? So Shani.
Oh, she promised me to come, but I don't know idea. What is that?
I don't know.
Do you know?
We are the same physical class.
Then you better ask. Right, so it is 1930. Is it clear? Right. Then that is for so typically let's find the root mean square speed for nitrogen as well. Right, second question. Calculate the root mean square speed for nitrogen gas at 25 degrees Celsius. calculate the root mean square speed for nitrogen gas into gas at 25 degrees Celsius. Find it quickly. Now I'm not helping. I think it's 40. Did you get the So I was struggling with the square root thing. Right, okay. So I'll give you the answer. $515.8. For nitrogen, the answer will be 515.8. Right. So now we have discussed two examples. We found the square root mean square speed of hydrogen gas and nitrogen gas separately. Now for hydrogen, we saw that the value was 1930, and for nitrogen, the value was 515.8. Right. So two different values. Now that means at the same temperature, depending on the type of gas, the root mean square speed changes. Is it clear? Right. Okay. Then you can note down in a separate point. According to the above two examples, according to the above two examples, it is clear that according to the above two examples, it is clear that the heavier molecules the heavier molecules move slowly. The heavier molecules move slowly, while the lighter molecules move at very high speeds. At very high speeds to achieve the same kinetic energy. At very high speeds to achieve the same kinetic energy. So the kinetic energy is directly related to the kinetic energy is directly related to the temperature and it can be proved as follows. So let's prove that. You can note down using the equation of electromagnetic theory. Now we are going to prove. can say using the equation of molecular kinetic. We can apply E equals 1/3 MNC square. Right. Now what we are going to do there is we are going to rearrange the equation by multiplying the equation by 2 and dividing it by 2. Okay. So let's start the equation. So we are going to rearrange. Rearrange the equation 1 by multiplying by 2 and dividing by 2. There's no exchange. They can be divided, they can be minus of n, but we are making a difference. So we can say PV equals 1/3 into 2/2 into MNC square. Then we know that kinetic energy of a particular gas equals to half mv square. So it is half mc square by this. Right. So we can say that kinetic energy is like this. Now here we have half m and c square by is there. So we can rearrange this equation, that is 2/3 into n into half mc square. So we can say PV equals 2n/3 into KE. KE is the kinetic energy of the gas molecule. Right. So then assuming the ideal behavior, you can apply PV equals NR PV equals NR. Right. So let's say this is the equation number 2 and this is the equation number 3. So we can equalize 2 and 3. Yeah. NRT equals to 2n/3 into kinetic energy. Right. So then we can subject kinetic energy. That is 3 nRT over 2n. Is it clear? Right there. Actually, there's a constant called Boltzmann constant, that is Kb. Kb, that is equals to nR over capital N. Simple nR divided by capital N. So therefore, kinetic energy equals 3/2 this one nR over N. Therefore, kinetic energy equals 3 over 2 kb times. So kb is the Boltzmann constant. Alright, so that equation we can use in directly. Now this is for one gas molecule, because we have used capital N. For one gas molecule. Now we know that there are Avogadro number of molecules in 1 mole. We know that there are Avogadro number of molecules in 1 mole. Then we can say, so for 1 mole of gas, kinetic energy is equal to 3 over 2 kb times P into in A. In A is the Avogadro number. Okay. Now we know that in 1 mole, kb means Nr divided by Na, right? Why is that? Oh, sorry, I forgot. Why this capital N became same name? According to Boltzmann constant, Nr over N is kb. But we consider 1 mole. In 1 mole, we have Avogadro number of molecules. That's why this capital N becomes Na. Then we can cancel off Na to Na. And since we consider only 1 mole, simple N will become 1. So we can say, therefore, kinetic energy equals to 3 over 2 times R. It's a bit because simple N will also become 1. Then for 1 mole of a gas, we can find the kinetic energy as 3 over 2 RT. If you can remember, that was the equation I gave you at the third positive rate in the fine molecular theory. About 2 hours before. Yes. If you turn to the page that we have written here. I told you that I'm deriving this at the latter part of the lecture. Yeah. So here, so kinetic energy of 1 mole of a gas equals to 3 over 2 times RT. R is the universal gas constant and T is the temperature. Then for one gas molecule, it is 3 over 2 kb times T. Is it clear? Right. So you can put it. quickly copy it down and then you can take a small break. If you take more time, your break will be short.
So,
Yeah.
in that question, what is the value inside the loop?
Which question?
Define the mean square speed of mind.
I can't remember. Wait. One hundred 66,071.
Then the root is changing. $516.4 billion.
No, 15.8.
I'm with $516.4 billion.
The temperature.
20. The 25. 290.
Then the thing inside the root is the same thing.
Right, that might be some error in your calculation. It's okay, we just wanted to get some idea about the values. Right, have you finished copying now? Then we can take a 5-minute break. Just fine. The time is 4:40 now. We will start at 4:45. Right? I have been spoken all this time while muting my phone.
For next week, we will have a video, right?
Sorry?
For next week, we will have a video.
And you don't need video?
No, but it's a bit good, like review it the day before.
Okay, we'll see. I'll give the video, but some sound parts may be not there. It's okay, we'll see. Okay, you can take your break. One another.
Maybe 5 minutes there.
කොච්චරක් වුණා?
Eka.
10 minutes. 10 minutes. Other classes වලගේ half an hour දීලා තියෙනවා නේ.
The classes.
They don't need. I know.
No, only in physics class. Yeah.
Right, so 10 minutes break is there. All right, now we learned about the mean square speeds and how they are being changed with the molar mass and the temperature. All right. Then the next one we need to learn is the Maxwell-Boltzmann distribution. Right. So we are going to learn the Maxwell-Boltzmann distribution of a gas. Actually, now we learned that the gases have no specific speed. Their speeds are different. Is it clear? The gases have different speeds. Is it clear? Right. So they are being distributed according to a bell-shaped curve.
Also, what is the shape of B? When you are down in the calculation,
Shape of
orbital B.
d orbital.
Yeah.
Usually it's not being specified because it has a very complex shape.
But that is to be just like it is like two diamonds to get it under 4 crore money. And the next is like another million.
Even the scientists are refusing to give a shape for that.
And these people will say
Because it is complicated. It's clearly mentioned that it's not fair to give a shape for d and f orbitals.
yes. Today during the paper discussion,
You might have seen it in Facebook or Instagram.
Magic for real said that it is the shape.
For real, their shape is not being specified. Right, okay. So now we are going to discuss the distributions of these speeds. Huh? Did you discuss this lesson in the school?
We done that kind of energy fish.
equation molecular conductivity. No, your school teacher is very slow.
Things we will pay. Today we did the paper before interval.
She has called me once. I was very slow.
Yeah. She said, "Sir, with the tip pick up the I in the first lesson because I is
Yeah. So then, why she is spending a whole term for the third unit? Yeah, 4 minutes.
He was like, "You wasted your time. You should have finished third in the last."
Right, okay. So we are completing this fourth unit during 3 weeks. Huh? And this is the third week. Today we are ending of this.
Fourth lesson.
Yeah.
For real?
Yeah, we are in the last part. After the Maxwell Molvar Rosman distribution, we are learning the phase diagram of carbon dioxide. Then that's all. Yes. Don't be amused. That's all. It's a very small lesson.
අර සංගීත මෙහෙනම් හරි ඩේට් තමයි.
Even I thought,
ස්කූල් එකට සංගීත මෙයා වෙන රෝච් කේස් එකේ ඉන්න ප්‍රින්සිපල් ඔෆිස් එකටයි අරගෙන ටයිම් එකටයි කැරිසල්
I told them right. Okay, so let's learn about this Maxwell-Boltzmann distribution. Right. So I told you, usually the gas molecules they do not have a specific speed. They have varying speeds. Their speeds are varying. Therefore, they have a bell-shaped distribution of the speeds. Right. So, did you write the topic Maxwell-Boltzmann distribution? Maxwell-Boltzmann distribution. You can note down from the above two examples. From the above two examples, we found that from the above two examples, we found that the root mean square speed of hydrogen gas was 1930 meters per second. H2 was 1930 meters per second. And nitrogen was 515, right? 515.8.
Answer. My answer is coming the calculators. I mean, came over here.
515 meters per second. 515.8 meters per second. Did you write it? What's the answer?
I have 16.8. Take it down. Is it good thing?
What do I say? It's 266,071, not 701. You have interchanged 0 and 7.
Yes.
Okay, so let's come. So those are mathematical errors, are not chemistry things. So I'm not responsible for those mistakes. Right. So now we are going to learn the Maxwell-Boltzmann distribution. Now we found that hydrogen has 1930. Now listen carefully. Hydrogen has 1930 and nitrogen has 515.8. Okay, that was their root mean square speeds. Is it clear? So that is the average one. That means average is the speed that the highest number of gas molecules reach. වැඩිම gas molecules ගන්නකට තියෙන speed එක තමයි. That doesn't mean that there are no gas molecules with lesser speeds than that value and the higher speed than that value. Is it clear? So that value is the value where the maximum number of gas molecules occupy by the speed. Is it clear? So therefore, we can draw the Maxwell-Boltzmann distribution like this. Molecular speed meters per second, and here will be the fraction of molecules. Right. Yeah, the value will change like this. Okay. So this is the asymmetrical bell shape, and it is not a symmetrical bell. Asymmetrical bell shape. Bells done one. Bell like a shape. Bells are like this. This is the bell. There's inside part. So this is a symmetrical one. Asymmetrical again make other way. The new symbol of KUP. Earlier it was symmetrical, it becomes asymmetrical. Right. That is unwanted factor. Right. Then, so this is called asymmetrical bell shape. Is it clear? Right. So this is the right. So this is the molecule speed. The highest fraction of molecules have. That is the peak. So that is the root mean square speed that we calculate. Then there are some other factors. That means there are some other fractions of molecules that have speeds that are higher than that of the root mean square speed and lesser than the root mean square speed.
So there are some molecules that are steel also.
Yeah, zero. A very trace amount is that last thing. Is it clear? So then that means the molecules with the lowest energy as well as the highest energy are minimum. The majority of the molecules are having the average speed. Is it clear? So usually the shape will be like this. Now let's say this is at 300 Kelvin. And this is at 300 Kelvin. Now usually once we increase the temperature, what will happen? If we increase the temperature, what will happen to the kinetic energy of the particles? They will increase. That means the fraction of molecules that are having higher molecular speeds will increase. So the higher molecular speed is to this side. So what will happen? The fraction of molecules with higher molecular speeds will increase. Like this.
For curve would increase.
Now let's say this is at 500 Kelvin. Sorry, which curve? Second curve, yeah.
Would it increase?
Yeah, it has increased. That means now the area under each curve has to be the same because the numbers of molecules will be the same. From the area it gives the numbers of molecules.
Marisa, what does that axis mean?
Which axis?
Y axis.
Fraction of molecules.
Here, is it a fraction?
Yes. The total fraction of molecules out of total molecules. If there are 1,000 molecules,
Yeah.
taking 10 fraction here.
Thank you.
Come on, fraction can bhagya.
Then Bhagya, Vidraya, PK,
No, the fraction has different variations. Without metama highest molecular fraction. Method fraction of molecules, the highest molecular fraction is over here.
Yeah.
So take a root means translated.
Hari, I mean, what is fraction?
I think I can simplify that because in a gas sample there are millions of molecules.
Yeah.
जब अपने millions का ना कोई अपने y-axis से alien में है, so we are taking the simplest fraction.
So if 1,000 now, what do you get? By peak, how
Yeah. Now if there are 400 out of 1,000 at this peak, then we can simply say the fraction as 4/10.
by axis on the right fraction.
Yes. Ask me that some page and page in the question. Main factors, right? So is it clear now? Once we increase the temperature, the fraction of molecules that are having the highest, that means highest fraction of molecules with the root mean square speed will be increased. Now see, here the molecular speed is higher at the peak. If we increase the temperature further, what will happen?
So it means how much we increase the temperature, there's still going to be at least one molecule that is still.
Yeah. So this is called, now this is a mathematical distribution curve. Right. So this is called the Maxwell-Boltzmann distribution curve. Is it clear? Right. So let's write down. So we have written that the hydrogen and nitrogen having different speeds, no? Right. Then you can say there's a distribution of speeds. There's a distribution of speeds from 0 to the values considerably above. From 0 to the values considerably above the root mean square speed. Considerably above the root mean square speed. Then you can say this is because the individual molecules collide and exchange energy while varying their speeds.
Right?
While varying their speeds.
We think the remaining can't be seen. But Even now, if there are alkaline elements passes from it, they can't be stable. Even
Then what will happen to the molecule that comes with energy?
if you not stable. ഒക്കൊമ്പത് എങ്ങനെയാണ്
Occur in natural possibilities. There's a small fraction of molecules that are staying still.
even in very high temperatures?
Yes.
I mean, that is a normal thing.
Now think of the students in a class. Class එකේ අනිත් ළමයි ඔක්කොම ground එකට ගිහිල්ලා සෙල්ලම් කරද්දි class එකට එන ළමයි නැති. ආයෙම නැද්ද? අනිත් හැමෝම අනිත් හැමෝම class එකට ඉගෙන ගන්නකොට කොහේ හරි round ගහන එකක් නැද්ද? Right. Exceptions නේ. ඒ වගේ තමයි.
Now not solid, now incident.
Those are natural things, natural incidents, natural distributions. Right. So you can draw this.
I understood it.
Yeah, I also understood it.
But in the class,
Then se traffic period active. So if we have to contain another same amount as
right, high pitch story. So that is the Maxwell-Boltzmann distribution of for nitrogen gas at different temperatures. Right, finish. Then let's move on. Then you can say four different gases are at same temperature. Four different gases at same temperature. The distribution can be given. The distribution can be given or can be shown as follows. Right, so it's like this. Like this. So once the molar mass is less, they are having higher speeds. Okay. Now this is at the same temperature. Let's say this is at 300 Kelvin. So at 300 Kelvin, the distribution is like this for different gases. Once the molar mass is high, they are having less molecular mass. The higher fraction of molecules are having low speeds. So once the molar mass is small, there will be high fraction of molecules with higher speeds. Is it clear? If we consider the examples, N2 and H2, molar mass of N2 is higher. So that means it has lesser speeds, 550. If we consider hydrogen, it's having 1930. So it has higher molecular speeds. There's a higher fraction of molecules with higher molecular speeds. Right, you can draw this diagram. Right. So that is a Maxwell-Boltzmann distribution. Next thing that we are learning is compressibility factor. Right on the subtopic, compressibility factor. That is capital Z. Z equals to EB over NRT. Right. Did you write the topic? Right. Then you can say the compressibility factor is used. The compressibility factor is used as one of the measures. The compressibility factor is used as one of the measures of the deviation of a real gas from an ideal gas. Of a real gas from an ideal gas. I say for an ideal gas, the compressibility factor capital Z equals to 1.0.
Compressibility factor equals
To 1.0. Then you can say this can be shown graphically. Once we plot the compressibility factor against the pressure. Once we plot the compressibility factor against the pressure. Right, so you can show it like that. For an ideal gas, it does not change. It's a constant at 1.0. Right, then you can note down in a separate point the deviation from the ideal behavior the deviation from the ideal behavior can be clearly seen when the pressure versus volume plot is considered. In a new point, you can say if we compare the behavior of real gases with ideal gases, if we compare the behavior of real gases with ideal gases, comma, at high temperature, the intermolecular attractions will become weak. The intermolecular attractions will become weak, and pressure will be increased. And the pressure will be increased. As a result, the PV factor of the equation increases. The PV factor of the equation become increased. And shows a positive deviation from the ideal behavior. Shows a positive deviation from the ideal behavior. In a new point, you can write down. If we consider several gases at the same temperature, right, now this is ideal gas. Then if we consider different gases, I'll use different colors. Let's consider helium, hydrogen, methane, and carbon monoxide. So helium will be like this. If we consider hydrogen, it is lightweighted, so it shows more positive deviation than that of helium. Then if we consider methane and carbon monoxide, carbon monoxide is like this. And methane will be like this. See? Those are the deviations. Now here the negative deviation is the positive deviation. See, at lower pressures there will be a negative deviation, at high pressures a positive deviation. Is it clear? So that is for different gases at the same temperature. You can draw this. Right, finished. Right. So let's see the next instance. Now we are going to consider the same gas at different temperatures. Right. You can note down. If we consider the same gas at different temperatures, if we consider the same gas at different temperatures, the compressibility factor changes as follows. Now we are going to consider methane gas. So this will be at 200 Kelvin, low temperatures like 200. So if we increase the temperature, that will be changed like this. $500, $650, and 1,000. Like this. See, once we increase the temperature, it comes closer to the ideal equilibrium. Then write a small sentence. At very high temperatures and lower pressure, at very high temperatures and lower pressures, the real gases, the real gases tend to behave as ideal gases. The real gases tend to behave as ideal gases. Is it clear? Right. Then there's a small part remaining that is regarding the van der Waals equation. That means they are under that part. Now listen. Under that part, we are going to learn the amendments that are going to be made with the ideal gas equation for the application of the real gases. Right. Right. We are going to learn the amendments that are being made for the ideal gas equation. That was explained by J.D. van der Waals. And we will be learning that part in the next week, and we will be doing some questions from this lesson.
In the same man, relevant secondary branch.
Yeah. Right. Okay. So in the next week class, then we'll be discussing that part, theory part, and we'll be doing more questions, and then that will be the end of the next lesson. And bring the tip I gave you today, energetics one. And we'll be starting energetics next week. Right.
So Francis, can you fix the hardest, right?
Which one?
Analytics.
Energetics is the easiest one. Yes.
Good.
Yes.
The next one, the right?
The hardest.
It's the hardest.
Especially the
Yeah, everyone will like chemistry, AC, organic, very the pattern that we did.
Who says that? Okay, that's the end of the class. Let's meet on next week. Huh?